Hey everybody, it's John from Additive Alliance with another installment on my series about building 3D printers. Today I want to talk about stepper motors and all the thousands of options you have when selecting what kind of stepper motor you use on your 3D printer. They of course come in many shapes, sizes, powers, qualities, and configurations. So let me turn the phone around, I'll show you some samples I have on hand, and we'll talk through it. So the first thing you really need to realize about steppers is they come in a huge variety of shapes and sizes, and you'll want to get a stepper that can easily be compatible with the hardware, electronics that you're going to drive it. So you want a stepper that's compatible with the stepper drivers like the 2209 or say a Tiny G that I talked about in motion control video. But you also need one that will meet your physical requirement as well as the power requirement, the loads you're trying to move. The first thing you need to think about is the load you're trying to move, so the weight or the size of the stepper. And most 3D printers use NEMA 17s, and a 17 just means that it's 1.7 inches across its width. So here's a classic NEMA 1.17 by Stepper Online. You can see that right there. And that means it's 1.7 inches from this side to this side, this side to this side. The height depends on the number of windings you get, and that will control the amount of strength. For example, you can see this one's a pretty beefy one, and here's one that's kind of a pancake. So this one has a lot less holding torque or general driving torque than this one does. And so you're going to have to look at the torque specification and figure out which ones you need, and basically look at other designs as a starting point and adjust from there. All stepper motors should come with a spec sheet, or at least one online that you can look up, and they'll give you all the juicy tidbits like the amps per phase and resistance per phase and step angles. Virtually all of these are 1.8 degree step angle, which means it's 200 steps per revolution raw. Most drivers allow you to use some form of micro stepping, which can be 2, 4, 8, even more, 16. Typical is 8 and very common, and you can find that with almost any driver these days. And what's important there is that it means that your inherent resolution goes way up. So if you have 200 counts per revolution times 8, you now have 1600 counts per revolution. And let's say you're using a 10 millimeter diameter pulley on that motor, that translates to a precision per step or micro step of about 20 microns. That's more than adequate. Your FDM head will not be able to flow within that boundary, so that's going to be more than good enough until we find some way to create FDM heads that put out super precision amounts of material, which we're not quite there yet. But the next thing you need to know is how fast you want to drive it. And this takes a little digging because a lot of stepper motors don't easily provide their torque versus RPM curve. As I mentioned, the torque of a stepper motor will drop off as the RPMs increase. So if you have a machine that's say above 500 RPMs, and again with our 10 millimeter pulley example, that's say about 200 millimeters per second, your torque is going to start dropping off. And this is going to be dependent on the friction of your bearing system. You're really not going to be worrying about acceleration because that's going to happen back here when the motor's starting up at low RPM. But your friction will be increasing, your frictional force will be increasing as you go faster. And so when you're way out here and trying to do 500 millimeters per second, you got to have a motor that's going to be strong enough. The other interesting thing you want to look for is flatness. Just like any kind of a good race car, you want a flat torque curve. Ideally flat up to some certain speed. It'll give you the most reliable performance on the unit when it's doing some really tight cornering versus doing long straights. So once you go ahead and find a motor that can meet your size, initial torque, and speed requirements, you've got to think about the configuration you're going to use. And I'll show you some different configurations. Here's a tiny little NEMA 8.8 technically, that has a hard mounted lead screw. It's called captive because the lead screw is fixed into this. In other words, as I turn the lead screw, it's not going through the motor at all, and it's going to turn, it's going to have this fixed, so as I turn the lead screw, it's going to move the coupling back or forth, and you notice it's very fine pitch there. So the other part of this is that you would have to get the specification to the lead screw along with the motor to understand what your linear movement is going to be. Here's another example. You can see this is a little stronger motor, but it's coupled to a gear reducer. And you can get a whole variety of different gear reducers, which you would likely mount to either a pulley or a flexible coupling here. So this thing has an enormous amount of torque, but it turns very slowly. So you can fit it in a tight space if you don't need to move fast. Here's a variety of 14s, i.e. 1.4 inches across. This is an interesting one because this is called a non-captive stepper motor. If you notice, as the motor would turn, the lead screw actually goes all the way through the motor. So you could actually hard mount the lead screw and have the motor mounted to something, and it would be going back and forth while the lead screw is stationary. Or you can actually hard mount this and have the lead screw pushing on something. Again, you can buy them with different gear reducers. You can buy them in a standard captive configuration, or say a more powerful captive configuration. Then you can get NEMA 17s. This particular one is the one I use for my X and Y. I use 2 of these on X and 1 of them on Y. My X has to drive the weight of the Y plus the weight of the Z, so that's why I use 2 of these. The Tiny G card is strong enough to do 2 of these at once, or it could even drive a 23, which is substantially bigger. You can see the difference there. Again, 2.3 inches across. But this is overkill. I don't need this for my system. I'm able to get up to well over 300 millimeters per second in motion, so I stick with the 17s. You can also buy 17s that have captive lead screws in them, such as this one. This is similar to what I use on the Z. This is a T8 4 lead screw, so it's 8 millimeter diameter and has 4 threads. And there's also going to be a spec on how many threads per millimeter it has. So you can get them with different lead screws. The ones I use on my Z are a little finer pitched than this. But you can see again that you can get a NEMA 17, and this is kind of a typical width. You can see my X and Y's are a little bigger width, a little stronger, a couple extra windings. I use 2 of these in my Z to lift it up and down. And you could even go as far as getting NEMA 23s, giant honkers with lead screws attached. And you can see how long this lead screw is. I think this is a 600 millimeter lead screw, maybe even longer, 700 millimeter. So you can get all kinds of configurations. The price on them is surprisingly inexpensive for the technology they are. You know, I think these motors cost me somewhere around 12 bucks, maybe $14 each. Surprisingly, these guys get more expensive because I think they're a little more exotic. So these are upwards of $30 each. But these are so ubiquitous and so common that you can get them relatively inexpensive. So that's a real quick take on stepper motors. If you have any questions, comments, you want to know more than happy to share. I have a lot of experience with all of these types of stepper motors, unfortunately, or fortunately. So let me know what you think, and I'm more than happy to answer any questions. Cheers.